Bismillahirrahmanirrahim. Okay, so let us start with our fifth lecture, and the fifth lecture will be article number 2.2, the Schrodinger's equations. So this lecture will be a short lectures or Schrodinger equations. The Schrodinger's wave equation is one of the fundamental formulas or the fundamental equations for quantum mechanics. So we know that the quantum mechanics or the basis of quantum mechanics is uh, the quanta, the concept of quanta introduced by Planck. Next, the wave particle duality, that one is introduced by de Broglie, and the wave particle duality, which one is explained by Heisenberg. And these total three things, these total three conceptual things is described by Mr. Schrodinger, and this can be this wave theory is described by Schrodinger's wave equations. So let's start from article number 2.2.1. That one is the wave equations. The one dimensional non-relativistic Schrodinger's wave equation is given by. So this one is the simplest versions of the Schrodinger wave equations. That one is h minus h naught square divided by 2m multiplied with second order derivative with respect to this one is known as psi xt plus v of x, then psi of xt equals to j h naught first order derivative of psi of xt. Now, what is psi of xt? So this psi of xt is the wave functions. Then v of x is the potential functions, and we assume that that one is independent of time. So look, so in this wave equations, we know that uh, uh, from the uh, modern physics concept, we know that there are two variables. That one is the positions variable, and also another one is the time variable. So in these Schrodinger's equations, we have this wave functions. We have this wave function, which one is simultaneously functions of time, and also x is defined as the functions of positions. Next one is the m is the mass of the particle. So j is the, j is the imaginary constant minus root over minus 1, and these are the basic postulates of quantum mechanics. Okay, now this psi of xt is describe the behavior of the system, and mathematically this psi of xt is a complex quantity. Okay, now let us solve the Schrodinger's equations. So we assume that the solution of the Schrodinger's wave equation will be psi of xt, which can be written in the form of psi of x and phi of t. So where we use these things using the separation of the variable method. So psi of x, that one is the independently variable with respect to x, and phi of t, that one is the variable with respect to time. Now if we put this value of psi of xt in our equation number 2.6, then what will happen? So this one, as because this one is the derivative, so this one is the derivative with respect to x, so the time variable will be a constant variable, so that one should comes outside. So only the psi of x with respect to second order derivative of x will be there. And we know that as because psi of x is assumed as the psi of x into phi of t. Next, in the right side portions of this equal sign, we know that that one is a variable with respect to time. So the psi of x will be the constant term, so that one comes out, and only the first derivative will be there. Now, if we divide this equation number 2.8 by 2.7, then what we will get? So psi, if we divide by psi of x and psi of t, so then this phi of t will cancel, so only the psi of x will be there. Similarly, v of x will be there, and the rest of the things will be cancelled out. So this should be 1 by phi of t. So now we can solve these things. We know that we can solve these things using the two portions, or the that means first of all we will consider that the time independent portions. That means the this one is the time dependent portions, and this one is the time independent portion. So if we write that the solution of this time, uh, that means that time dependent portions, that solution of this one is defined by eta, and also we can and this will be defined by e. So let us solve these things. So if we solve this equations number 2.10, then what will happen? Look, 1 by x, that means dx by x. If we integrate these things, then what will happen? Ln of x, right? So that one will be phi of t, ln of phi of t. So that one will give us ln of phi of t should be equals to minus j e divided by ht. So this part. So if we take the inverse of ln, then that one will be phi of t should be equals to e to the power minus j e divided by ht, where this eta by h bar, this formula comes, comes from, we know that e equals to h nu, and nu is the angular, nu is the frequency. So if we define these things frequency in terms of angular motions, then omega divided by 2 pi. So h divided by 2 pi is equals to h bar, right? So we can write down omega should be equals to eta divided by h bar should be equals to e divided by h bar. As simple as that. Now, so this one is the solutions for the time dependent portions. Similarly, for the time independent portions or the position dependent portions, if we assume that one equals to e, then we can easily solve this thing. This one is a second order, so our second equation should looks like this, and we know how to solve these equations from our mathematical background. So try to solve these things. So this equation is something like this. dd of second derivative of x, or let us assume that one is y, second derivative of y, plus a y equals to 0. And you know, you have to consider that one is m square, one constant. So if uh, you cannot solve these equations, then we will discuss these things in our problem solving class. And this I think this solution is already shown at the end of our book. That one is in appendix E. Now the next one is the physical meaning of these wave functions, article number 2.2. So physical meaning is that we are ultimately trying to use the wave functions phi xt to describe the behavior of an electron in a crystal, right? This functions phi of xt is an wave function. So it is reasonable to ask what is the relationship between the function and the electrons. That means this question should come. Then what is the relationship between the functions and the function and the electron? The total wave function is the product of the position dependent or time independent functions, and the time dependent functions. So that one should be equals to psi of xt. So you separately write down these things. So psi of x, put this thing psi of x is constant. So phi of t will be like this. We have solved this. We solved the equations and we found that phi of t equals to e to the power minus j e divided by h bar h naught t. Now, if we assume that psi of x and t whole square, then we have to as because this one is a complex quantity. So one will be the these two should be complex conjugate, right? So we know that the complex conjugate is defined. One will be simple versions of psi of xt, and another will be the uh, conjugate or the asterisk sign of psi of xt. Now, psi of xt means if that one is the minus sign, if that one is the minus sign, so psi of xt will be the conjugate, means that one should be plus sign. So if we write down psi of xt with the asterisk sign of or the conjugate of the psi of xt, then that one will be psi of x and asterisk of psi of x, if that one is a time independent variable. So psi of xt equals to asterisk sign. So whenever again these two are in the conjugate format, so psi of xt should be equals to psi of x square, and this one is a time independent variable. So the one major difference between the classical and the quantum mechanics is that in classical mechanics, the position of the particle or the body can be determined precisely. In classical mechanics, we can easily determine the positions of the body. Whereas in quantum mechanics, the positions of the particle is found in terms of probability. We have discussed this thing in our last lecture. Okay. Now that there are two boundary conditions for Schrodinger's equations, the first boundary condition is the integration from minus infinity to infinite psi of x square dx should be equals to 1. This one is the first boundary conditions. So in this, this can be defined as the boundary condition psi of x must be finite, single value, and this one should be continuous. The second condition is derivative of psi of x must be finite, single value, and the continuous. So these two are the boundary conditions. This one up to before article number 2.3, it will be the end of our fifth lectures. So in our next lecture, we will start from article number 2.3 or the applications of Schrodinger's wave equations. So your fifth lecture will be concluded here. So we'll discuss these things in our problem solving class tomorrow. So in the next lectures, I will try to discuss from I will start from article number 2.3 or the applications of Schrodinger's wave equations. So up to this, please go through these lectures and we can discuss these things in our problem solving class. So thank you.